Alright, so go ahead and draw the can. Draw your 20 X's, or your 10 X's, your 20 O's after 2 minutes. Where would they be?
That's a good answer.
Thank you. What about the water? X's. Where are
There's
they?
like a few at the bottom and then they all
Wrong answer.
Turn it
I
there.
mean, it turns to
Okay, so how do we work with this? So how about you start us off? What do you think if I started with my 10 X's here at the bottom of the can? And what do you think is going to, actually let me just draw my 20 O's too. Okay, so what do you think is going to happen as we heat this up?
X's are gonna go.
Maple Valley's.
Okay, I know it's Friday. Let's focus on this, please. What's going to happen to my X's and my O's after 2 minutes of boiling?
We'll get hugging kisses.
The X's are gonna go to space and they're gonna become.
Okay, so some of these X's are going to do what?
Come steam.
They're going to become steam. So how can I change my picture now? What would I do with some of these X's?
Draw them like
Erase some X.
and then
Erase
draw
them,
them
put them up there.
all around the can.
Okay, so all of them? Should I erase all?
No, some.
Okay, so how many?
5.
Okay, so why are we leaving some at the bottom?
There's still water.
And all the water evaporates.
Okay, so not all the water has changed to steam yet. It hasn't gone through that phase change, Michael? Now what?
Now draw some like arrows for the.
No, I want to actually hear from one of those two gentlemen at the table.
Draw arrows going up and down around the can.
And what does that represent?
The steam,
Okay, so what about the steam?
because it's warming up the water.
Okay, but I'm using X's to represent steam. Why am I using X's?
Because water that's heated up turn to steam gases.
Okay,
phases.
so we're showing it, and so you want me to add arrows to show that it's moving around. It's not just hanging out in there. Okay. How else can I change this picture here? It's been boiling for 2 minutes. What else would you expect to see?
The air circle.
What?
The air circle. Some air
Draw a
circle.
circle.
Yeah.
Okay, so some air would exit the can. Why do you think it would do that?
Because
Okay, it's being forced out somehow. So how many O's do you think might we want to remove from this can?
9.
Okay. Okay, so let's take out some of these. Okay, so what do you think about this drawing? Vernon, what do you think about this drawing?
They look wonderful.
Okay, so you think it's a pretty good explanation of what would happen?
It's a good thing.
No? You don't think so? What would you change, Andrea?
I think some gas should be escaping out of the can as well.
Some gas of what? So some X's could probably exit the can too. Okay. So let's take out a few of those X's. Does anybody else want to change anything about this drawing?
Put it on the side of it.
What do you mean?
There's air always around anything.
Okay, so maybe we should have started with some extra air molecules around the can because there's always air around a can.
Yeah.
Okay. Anything else that you want to change about this drawing?
Water.
What about the water?
Should be spread out.
Oh, okay, so the water's not going to just be...
Yeah.
Okay. Anything else?
Unless there's a rock in there.
Okay. Okay.
I think there should be more air inside the can, because now it looks like the air on the outside is overpowering the air on the inside.
Okay, and so how could I draw that?
By putting air inside the can.
Okay. So how and was that? Do you think that's all just the air that it started with?
No, not necessarily. It could be air that was on the outside going inside.
Okay. So maybe some air also went into the can from outside. So I think her point is really important because she said it looks like right now there's more air outside the can, and why would that be a problem?
Because then the can would be getting crushed, or at least a little bit crushed maybe.
Okay.
Because it wouldn't be balanced.
Okay, so we're looking to have that balance of pressure from inside and outside. If one side has more pressure than the other, we're going to expect that thing to crush, or like the balloon to deflate or implode. So it's important to show in your picture, just like she said, that we're looking for these balances of pressure. But I also think it's important to remember that as it heats up, those air molecules inside the can are heating up and they can exit the can too. So you should be thinking about, does the total number of gas molecules, like what would the total number of gas molecules look like in your can as you heat it up? And is the amount of air inside that can changing from, like our first can, we had, let's say we had those 20 air molecules and we had the 10. And now I've heated it up. And then I flip it over. Okay, so this is stirred, this is heated, and this is flipped. So let's say we can jump ahead to flipped here. How many water molecules would, if we're still saying we started with 10 water molecules at the bottom and 20 oxygens, when I flip this can over, let's take some guesses about how many of each molecule would be in the can if we started with those numbers, those kind of numbers that we said we started with. What do you think when we flip it over? Did the number of air molecules change in that can, do you think? Did the number of water molecules change in that can? So tell somebody next to you what you think. Take a little guess about that.
Water 1 and 2. That's Justin.
Justin, what do you think? What do you think?
The temperature will decrease.
Okay, the temperature decreases, but let's talk about the number of molecules in there. Do you think that changed, the number of gas molecules?
I'm hot.
The air or the water?
Yeah.
So yes, why?
Because pressure. Because when the temperature decreases, the air molecules also decrease.
The number of air molecules decreases when the temperature decreases?
Yes.
Okay, how does it decrease?
Give me a second.
You flip it, right?
Okay, I flipped it here. What's happening to the number of molecules just from here to here? Is the number of molecules going to change?
There might be
No.
some, that's why.
They're just slowing down.
Okay, so the number wouldn't change from here to here because temperature is not changing the number of molecules, right?
No.
Okay. But I guess what I want you to keep thinking about is when we started with this 10 and this 20, do you think that any of this 20 like escaped? And so maybe here there would be maybe less air, so maybe 15 air molecules, and still like we had 2 waters here and maybe 8 here. Do you think that's possible that some air is pushed out of the can
Yeah, but when you're going back, you put it,
when I flip it back over?
yeah,
How?
you're capturing the air back.
And so maybe air is getting, how would it be captured?
No, because you're just still with the air there, and then when you go like this, you just capture the air.
Okay, so the can is open, and when you flip it over, maybe you could be capturing more air, but let's think about air pressure. You have this air pressure that's always around the can, so is turning a can over changing the amount of pressure that that air is putting to go into the can? Is the air pressure changing? Like, would more air enter the can if I have it this way or this way? I have a can right here. Can more air enter the can now or now?
Same.
So if I hold the can like this and I hold the can like this, is the amount of air that could enter this can the same or different? Why?
It feels different when I heat it cold or cold.
Okay, so if less air could enter this can right now, we would expect that the pressure here would be more. So it would make it crush. That's his idea. So yeah, we can assume that the amount of air that could enter the can open or close is going to be the same. So I don't think that just flipping the can is capturing more air. Whatever you have here should be about the same as when you flip it over. Okay, I think maybe this, I want you to keep that idea in mind, and I'll talk about it specifically with each of your posters that you're working on. I think that'll be easier to picture as we look at the drawings that you've started. As you finish your poster, at the bottom, I want you to include a written explanation about why the 3 cans had a different amount of crushing around it.
We try to put the same amount of air around each one. It's just the air outside the can. The air pressure always stays the same.
Okay. So this is while it's being, this is not while it's being heated yet?
No.
Okay, so you're going to have like start heated and then flipped?
Yeah.
Okay. So when you draw this one as being heated, how many of those X's are going to become steam?
Yeah, at least half of them.
Okay, and how about in this one?
Probably the same.
Okay, and that one?
Same.
Okay. And then what's going to be entering or exiting your can?
Air and some steam.
So some steam will be exiting. Do you think the amount of steam or the amount of air that would be exiting each can is going to be the same?
Probably not.
Why?
Because there's more space for it to go inside. Like this one would be easier for them to go from there to there than in the taller can. Because there's more space for it to go inside without leaving the can.
Okay, so which one's going to have more steam leaving the can?
Small one.
Okay. And which one's going to have more air leaving the can?
The large can.
Why?
It's bigger.
Because there's more air inside of it, so there's more that can get pushed out.
Okay, so what do you think the amount of space that's available inside the can has to do with it? So do you think the amount of space there is would affect how much could go in or out?
Oh yeah, because it could, even if they get pushed, it could still stay inside. So
Probably small.
maybe the small one. Have the most air come out of it.
The small
I'm
one?
not sure.
I'm not really sure either. So try to make sure that you,
You're not sure either? You asked this thing.
no, I'm trying to think through this with you. No. When he moves it from, or when you move it from this to this, when you flip it over, or you're not flipping it, you're just going from here to the water bath?
Yeah.
Is it going to be any different between here and here? What's inside the can?
Yep. They're gonna come out. What is that again? The water. The steam. The steam is gonna come out
When?
when the can touch the water.
It's not coming out here?
It is.
Okay, so in both the steam's coming out of the top of the can?
Yeah.
So is anything going to change from here to here?
No, it's just gonna be cold.
Okay, and what does being cold do to it?
Slows the air down. There'll be water molecules at the bottom instead of floating everywhere.
Okay, so some of these purple triangles are going to they're going to go to the bottom. So why doesn't this can crush?
Because it's not sealed.
Okay, but why does it matter that it's not sealed?
Because you're letting like air out or something.
Letting air out?
When air don't get to it,
Steam out.
it bursts. A star burst.
So when you flip it, air isn't getting in, but when you leave it open, air is getting in?
That's what we said.
So maybe there will be a difference between what you see inside here and what you see
yeah.
in here, right?
I think
Okay. So I'll come back and see if I can see. The escape?
They go around.
Yeah, I forgot how good. That's the good one.
Just like that.
Okay. So I'm still confused about, so I see that you're showing me big arrows outside, little arrows inside, the littlest arrows are here. But what I can't see from the picture quite yet is why does this one have the least amount of pressure inside the can? You can write an explanation underneath on the paper, that's fine, because I want to know the difference between the 3 cans anyway.
You write it.
You could
Write,
easily-
not speak.
Scooby-Doo.
Very cursive.
Why does that one have the least amount of pressure?
Because it got sucked out. I mean, because the can crushed, so it's out.
What's out?
The air
How did it get out?
through the water, and then it made bubbles and it popped out.
Okay. So your picture is trying to show it, but you're not using your picture, I don't think, to explain what's happening. So tell me about
Oh,
what could be causing pressure in this can, what could be causing pressure in this can, what could be causing pressure in this can.
That had been like 80 years. Yeah, oh, it goes, oh yeah, it was going, it goes.
What's causing pressure in this can?
Damn, no, I gotta go look it up on it.
There's steam in there. What is the steam doing?
Pressure moving around crazy.
Okay, and what is the air doing?
Well, you mean the
The air molecules. That's not the water molecules. The O's here. What are they doing?
so that's not steam.
Steam is the X's. Air is the O's. Like oxygen and like all this normal stuff that's in the air we breathe.
I hate you.
So I see in this picture that they're both moving around. So how is that different than that?
This has nothing pushing upon it, no pressure.
No pressure?
There's some pressure, but not as much pressure as this one.
Okay.
Where this one's pushing, there's people moving more rapidly, pushing out, compared to this one where there's only a few and it's not as strong.
Okay. And also, what's another difference between this and this?
Cans.
What's inside? What's another difference between what you drew here and what you drew here of inside the can?
Oh, there's no, yeah.
Okay, so this one, there's no steam molecules moving around. They all turn back to water. But in here, you do have some steam too. So now you need to explain why this can is crushing more than this can based on that. Tell me about the pressure inside the can, outside the can. Do you have the checklist from yesterday? Make sure that you've answered all those questions for each of your cans.
Checklist.
Like in the top part of the can. What's taking up space?
A lot of air.
Air and steam. Okay. And what's taking up space? Like when you flip it over. Oh, we didn't flip it here. So when we moved it from here to here, what do you think is the effect of taking these purple, the water molecules, and making them all be at the bottom? Does that change how much space is available in that can?
Yeah, so maybe more air has like more room to be in.
Could be. I mean, it kind of looks like that in your drawing here. It looks like air is taking up. It looks like there was maybe more air in the can. And so then what about pressure inside and outside the can?
It's equal.
Okay, so maybe, how can you show me that?
There's the same number of air molecules on the inside as on the outside.
Okay, so that's why?
Yeah.
So you counted?
Yeah, they're 15.
Okay, so the pressure, the arrows that are pushing against the can are equal to the arrows that are pushing against the can.
I didn't count the arrows, I just counted the stars.
But the arrows are what we use to represent pressure, right? Okay. And then you're going to do the sideways can. So let's talk about what's in this can right now. Woo! And it's kind of the same as this and this. They're all pretty much the same. So now we're going to turn the can sideways. What's going to happen?
It's going to be.
There's going to be more water in it because it did make that little sucking sound, so we think that a little bit of water, I think.
So, but why do you think that water can go into the can?
Because it's not sealed completely and it has room to go in.
Why does it have room?
Because the gas that was in the can is converted back into water. There's more space.
I don't get it. Like, if you would put like a regular can in the water, it wouldn't did that. It would have just.
Right. So yeah, what is the difference?
Heat. It's the heat.
So what about the heat?
I don't know. That's what I'm trying to still.
What did we do when we went from the hot plate to the cold water?
Change the temperature.
Change the temperature.
And what did that do to what was inside the can?
Put more pressure on it, or I don't know.
Okay, causing more pressure. And then you cool it down quickly. What happens to that steam?
It turns to a liquid.
And so what happens to the pressure then?
It gets more pressure.
More pressure? But all of a sudden these aren't up here anymore. They're down here. So what happens?
So the cold, it make it to liquid, so therefore the liquid, like the liquid goes to the bottom of the main can.
And so now we have that top of the can. And what happened, do you think, to the pressure at the top of the can? Inside the can? Or in this, like where you have the opening for the can? I guess another way to think about it is we've been talking about pressures, and anytime something is able to like force its way somewhere, is the pressure higher or lower?
pressure higher.
Okay, and so let's think about that water. What could you tell me about the pressure of that water compared to whatever was in that can?
I start hearing it.
I don't know.
Why could that water get into the can?
Because there's more space.
And what about pressure differences?
There's less pressure
Where?
inside of the can.
Why?
Because the air is cooled down, the water is cooled down, and it's turned back into a liquid, which means that there's no gas pressure, it's just air pressure. The air has more places to move around into, and it slows down, creating less pressure.
Okay. Air is a gas, but you're right. You have less pressure because the steam isn't there anymore.
Yeah.
Okay. Does that make sense? So can you summarize it now? Why is that water rushing into? Why is it rushing into that can?
It's taking up the space.
Taking up what space?
I don't know. I don't want to answer this. I don't.
Okay. How about you work on drawing the picture, and we'll come back and see if we can explain it with the picture.
Yeah.
Okay. So we started all with 17. Oh, okay. I see. And then 17 X's are still inside the can as we heated it up.
Yeah.
O's inside is 4, and then 7 left the can. Okay, and how did you just kind of, okay, let me,
I just thought that more than half would leave.
Okay, and then here we have 17 X's. Inside is 11, and then 11 left. Why?
Because I think with the medium can, it would be like half and half. Because there's still, like, this one a lot more left because there's not as much space in the can for the air to go.
Okay.
But this one there's more space, so only half of them left.
Okay, interesting. Okay, and then we get down here, and now when you flip it over, what happens?
They crushed.
Okay, why?
Because the steam touched cold air.
The steam what?
Touched cold water.
So what happened to the excess?
We haven't drawn it yet. I don't
Okay.
know.
We don't know what we should do.
So when you flipped it from hot into cold, what happened to the steam that was in that can?
It would all go to liquid and go to the
Okay.
bottom. But I don't know if it would leave the can or
Oh.
or if there would be more water going in. I'm not sure about that.
Let's say that, let's not worry about if any water was going in. Let's just talk about what was in the can. So you flip it over, you quickly seal it.
So then all the X's are
Yeah, let's say that they can all just go
Okay.
down there. So which can crush the most?
the medium one.
Okay, and so does what we have in the can, is that going to show that?
No. We're just going to show that this one crushed the most.
But so what causes more, like, okay.
Because there's more, that's what I was talking about, the ratio. There's more, like, I'm getting confused about the big one now. I think it's because the air to water, like, the water only takes up a certain amount of space in the medium can, so it can crush more. But in this one, the water takes up more of the can. And then in the large one, there's a lot more air, so that takes up more of the can too.
Okay, so the perfect ratio is that, I guess, yeah, show me what pressure has to do with this, I guess. So, what are those?
Water. Oh, yeah, steam, huh? Right?
There's not going to be steam in this one, so I'm going to erase those.
Wait, what?
Remember, because all the steam cools down and it goes to the bottom,
But then it's in the can.
but it's not going to be at the top.
She said wait until it's in the can, then when it touches the water.
And this is when it touches the water. So it's already touching the water. It's already had a chance to cool down. Okay. Okay, so you're going to show me the pressure. So based on the checklist, what's missing on these cans, and I think it's because you're still thinking about it, is there a pressure difference inside and outside the can, and why? Okay. So show me what's causing pressure outside the can, what's causing pressure inside the can, and is there a difference?
We don't know that.
Well, you do know a little bit because you have some evidence, like you saw what happened. So which one?
We only saw, but we don't know
Which
what
ones
happened.
seem to have the biggest pressure difference?
Middle.
Okay. So you think this one has the biggest difference in pressure, so you need to try to show me using your explanation here why that would have the biggest pressure difference. Okay?
Yes.
Okay. A lot less than...
Restaurant?
pressure in this can is a lot less than the pressure in the third can because
Whoever wrote that better finish it. That was Carson. No, Carson wrote that.
why is there less pressure inside of this can than the third can?
Because there's no steam.
Okay, so there's no steam.
Left, because it turned back into water, so therefore
Not
there's no
enough steam to put pressure onto the can, keeping it this full size.
Okay, and then can 2 is more like in the middle, has half molecules in air, the other half is back to water, therefore imploded, kind of like the halfway point you're saying.
I just told him to put this and this together.
Okay. Can 3 is one of the molecules putting pressure on the can, causing it to implode less. So, you're almost there, but tell me, why would it implode less? Like, what's going on outside the can? So in your written part down here, tell me, why does something
The same
crush?
amount of pressure outside as there inside. So there's not more, it gets equal either or.
Okay, so now water.
Either implode.
So add that to each of your 3, maybe Javier can write that. Okay, so what would cause a can to crush more than another can? Just like if we don't even think about your experiment, what would cause one can to crush more than another can?
Amount of space.
Well, what have we been talking about that causes things to implode or like change? Like when we did our balloon, why did we say that balloon would, or in that syringe or anything like that? What were we investigating?
The smaller the amount of the spaces, the more crushed the object will be. I don't know. I was talking about the marshmallow experiment.
Okay, so when we squished the syringe in the marshmallow experiment, we increased the pressure.
Because the amount of space decreased.
And so why did that marshmallow squish? What do we know about the pressure inside that marshmallow?
The air is probably like compacted.
It's trapped in, so it can't go nowhere.
Yes.
Okay, and could the marshmallow press, like, how is the pressure of this air versus the marshmallow? Which way would it go? This is the marshmallow, this is the air. Air pushes more. So in your pictures here, which one has air pushing more?
Outside.
Okay. Which can crush the most? Either one of these two?
Yeah.
So in your 2 pictures here, are you showing me anything about like outside air pressure versus inside air pressure, like why one would crush more than the other?
Why would I?
What?
What did you ask?
So
I'm wondering why it crushes.
So you're saying we should like put air molecules coming out of the can as well because it's pushing down the water, or
Okay, so let me look back at your heating pictures up here. Sorry. You said in this one we're heating it up more, so what happened in the can?
liquid turned into a gas.
Okay, and what else happened?
Air molecules and gas are floating around in the, well, not floating around, but moving around in the can.
And you also said more left the can. Look how much more stuff left the can, you said, right? So what would having more stuff leaving the can, how could that affect why that can would crush? If there's less stuff now in this can.
More water could get in.
So maybe that's why some more water came in. But also, why would it crush?
Because the air molecules are pushing into the can.
There's more air molecules outside than inside.
Yeah.
And it's
Yeah, more, and so,
stronger.
yeah, they push the can.
Okay. So can you maybe jot yourself a note right here to remember that for Monday?
Use pencil.
Okay.